what they are, how you can use them, and how to actually make them. So we're doing this slideshow because Robotics is given a grant by the Stanford Foundation to start a 2-year project that promotes the use of composites in beds. It started in December 2024. It's based off composite materials and carbon fiber. We as a team want to increase the use of these materials in beds. And what we're trying to do with this project is design lesson kits and activities to promote this use and send them around to teams across the web. Alright, let's start off with a little introductory again. Out of these 4 things, most groups treats a 1 to 2 by 4 concrete and carbon fiber, which makes a composite.
Out loud.
Yeah, out loud. Any answers?
The wood.
Okay, so you say what?
The Rice Krispies.
Okay.
It's the concrete because it's like a mix and gravel.
I think those answers. I'm going to tell you. It's actually all of them. It was a trick question. And here's why. Rice Krispie treats act like a composite due to being a mix of the rice puffs and the marshmallow, which the marshmallow holds it together and gives it a bit more structure, and then the rice strengthens it and makes it have a form that looks like you. Wood is a mix of plant fiber cells and then this natural polymer called lignin, which you can actually remove from the wood and tan it clear by consuming a different type of resin. Cement acts as a composite due to the cement being formed around rebar, which gives it strength and better resistance against like tension forces. And then carbon fiber, that's the type of composites we'll be talking about today. That's a fiber reinforced matrix. And that's a more traditional composite like fiberglass. So I'm going to tell you about composites. They're made from 2 different materials with different physical properties, which when you mix them together, they become stronger and have better qualities. These materials, in this case, fall into 2 categories: polymer matrices and fiber reinforcements. The fiber reinforcement materials can be man-made, like fiberglass, carbon fiber, additive, otherwise known as Kevlar, or natural, like hemp fibers. These provide strength and stiffness to the matrix, which polymer matrix, that's like the resin, which when you add them together, the resin allows for better load transfer and force distribution over the entire piece, and protects the fibers from outside materials, outside forces. Why you should use composites? They hold several advantages. They have a much better strength to weight ratio than things like metal or plastics. They have better resistance against tensile strength, so pulling and pushing. They're better against that, and they have better resistance to elements. Your composite materials, they aren't going to rust, they don't corrode. They're not going to like crumple because get wet. Composites are lightweight and very strong, and they should be able to withstand any of the forces they might experience at best. The best place to use them is on high-load parts because of how strong and lightweight they are. If it's moving especially far off your robot, there's going to be a lot of force on the entities. If you have carbon fiber, the lightweight means less forces are experienced so far. Like if you can arm something, if it's made of carbon fiber, it's not going to tip because it's so much lighter. So like using them on telescoping arms, for example, which our team did. And what year is this?
4 years ago, something like that.
Okay, it's like 2020, 2019. We used a telescoping arm made of carbon fiber just because of its benefits. We actually made this in here too. Board or anything like that. So it's good for telescoping arms and liners. But it will exert less force over your robot and whatever it's attached to at a minimal loss of strength compared to like aluminum or other metals. Here's some more details on the fiber reinforcement part of the matrices. They are incredibly big. Materials, length of the fibers themselves, the weave patterns, how they're interlocked, and like the thickness of each fiber. They can be divided into many different categories based on what materials they are. You have like fiberglass, carbon fibers, boron fibers, ceramic fibers, metal fibers, Kevlar fibers, and then natural fibers again. All have different properties, different strengths and weaknesses, different uses. And like I said, here are the properties and pages. And all of these fibers, they tend to be skin irritants in a similar way. Fiberglass insulates this. If you're working with these, you want to be proper PPE, safety glasses, gloves, respirators, depending on what you're doing. It's the best way to use them. So, out of these, which one should you not use? Another question.
The last one.
The toilet paper?
Yes.
Okay.
Does anybody else have any different opinion?
Any other guesses? Any other answers? Okay. This one isn't a good question. It's the toilet paper. So what I'm going to do now is show the strengths of all the other fibers and why you should use those. So first off, it's aramid, or otherwise known as Kevlar. She's not like natural vest just as a fiber, like bulletproof vest just as a fiber. So what it's good at, it's better against impacts and abrasions from carbon fiber. It's much tougher, but it has a low compressive strength and it's very hard to work with just because of that abrasion resistance. So you know, on the machine, on the cut, on the used. Next up, carbon fiber. It has the best strength and stiffness to weight ratio. You can see it a lot on robotics, and robotics is just one of the most common used ones. It tends to be more expensive than the other fibers, but it has a lot of benefits. Lastly is fiberglass, otherwise just known as glass. Very commonly used, lots of applications. You see in stuff like boats, bathtubs, pretty much everywhere, or just by itself as insulation. It has a light, it's pretty light, it's moderate strength, it's low cost to use, and it's high dependability, which matters when you're making a composite. Lastly, toilet paper. It's not very strong and stiff, very inconsistent, you can't control your breathe pattern on it, very thin, and it might interact well with some matrices, you know, turning into goo stuff actually, layering. And then what I'm going to go over now is the different patterns of carbon fiber. You can see here we have a few different ones. That's enough. We're going to pass those around so you can see them. Is
We have
terminology
some
about
ones
that.
made from glass or fiberglass.
So first off, it's
And then
called toe.
different
That's like
leaves
the
and
lines
the
filament.
actual carbon fiber.
That's what's like you're using. That's all going in the same direction. So you almost follow the line. Then that matters in the different types of weaving. That's the point where the different toes go under or over each other. That's a possible point of weakness. That's the stability. That's the ability to maintain the angle that's woven at without coming out of line. And then that matters when you're letting go of the different 3D shapes, like back and cause issues depending on what kind of movements you use. And then weave. That's just the orientation of the fibers, how they're interlocked, how they're joined together. So let me go to weave. Material volunteers some characteristic. However, many other characteristics can be altered or enhanced on the weaving material. Like these fibers, very similar to a fabric. Different patterns, they can be woven and change different things. We can affect things like load strength, tensile strength, because it determines how the force can be distributed over the surface. Now just some common examples of weaves. Starting from the left, that's called a plane weave. It's like a 1-to-1 over under ratio. It's very good at flat parts like this, or tubes like this, and then just simple 2D curves, not complex geometry. That's where it starts to struggle. It's going to have your highest stability, so it's pretty much always going to be in that pattern, but it's not really as great as other complex shapes. Next up, this is called a trill weave. It forms a bit of an arrowhead pattern over your carbon fiber. The common variations are 2x2 and 4x4. What that means is 2x2, it goes over 2 toes and then under 2 toes, and then 4x4 is the same thing, but just over 4 under 1. Next up is the satin carbon fiber weave. It gets its name after the similarly made silk satin fiber. It's the best at going over complex shapes. It drapes very easily compared to other forms. However, because of that, it loses a lot of stability, so you gotta be a little more careful when working with it, because it can easily fall out of line. Lastly, it's called the unidirectional carbon fiber. What that is, all of your toe is in a line, so there's no weaving in it. It has some benefits, but also weaknesses. Like if you're manufacturing it, some of it comes loose in the matrix, it can just pull out across all of the piece, whereas the other ones would have floppy to hold it in place. It's held in place like that by using a different material, like just kind of string through it on the ends. That tends to be, I think, nylon. And and that just ends up becoming a product of composite. When unidirectional is used, it tends to be sandwiched by 2 layers of a different weave at the top and bottom to negate some of those weaknesses. Well, actually, look at that. The last type is called a braided. It's not thin, but it's very similar to the drill weave. It's that instead of being at a 90-degree angle, it's at 45-degree angles, and it's extruded in a cylinder. So that's good. You see a lot of things like prosthetic limbs, or this very big cylindrical object, like this piece right here. This came off of a drone. It was made by wrapping 45 degrees braided on fiber around itself, around a balsa wood reinforcement in the middle, like a lightweight piece. Next up is the other part of the composite material, the upstream one. The other thing is the polymer matrix. There are several different types. You see epoxy resin a lot, vinyl ester, and polyester. Epoxy tends to be the overall best at the important categories. It's the strongest, has the best shelf life, and is the lowest rate, but it's expensive and very sensitive. Epoxy comes in 2 parts, so you have to mix those together at a very fine ratio for it to work as intended, and it releases a lot of heat as it's curing. Next is vinyl ester and polyester. They each have their own strengths and weaknesses. Resin is skin irritants and eye irritants, so like when working with the fibers, better eye protection, and gloves, and then they release a lot of fumes, so you would like in a well-ventilated area. That's not fun, having issues. So, to go into more detail about epoxy resin, it's the resin composite, has a high strength, low rate, which is what you want in a composite material, has a higher cost, and is sensitive to ratios, and releases a lot of heat as they're curing, but the benefits are much better than the negatives. It requires a specific hardener, but then that depends upon to epoxy, and releases, it's an exothermic reaction, so it releases lots of heat as it's curing, and it has the best shelf life out of the options. Next is polyester resin. It's cheap and easy to use, good for beginners. It's UV resistant, so if you're using it for any outdoor use, which I don't think you will in robotics, it won't yellow in the sunlight, or it will much slower compared to the other alternatives. It's a bit weaker than polyester and epoxy resin, but it also has a low corrosion resistance. Unlike epoxy resin though, it's cured by a catalyst, so mixed ratios has support for that. Next is vinyl ester. It's a bit of a middle ground view, less strength than epoxy, less cost than epoxy, stronger than polyester, more expensive than it. But it has the best resistances to very high temperature, but has a very limited shelf life, and is also cured by a catalyst. Okay. I have a few pieces of carbon fiber. This piece right here, it was made off of that mode about 2 days ago. It was made by a process called vacuum infusion. It's called the vacuum infusion process, which is but 2 kind of main ways to make carbon fiber pieces around the node. It's the vacuum infusion process and just regular wet layup. How vacuum infusion works, you take your dry fibers, place them into a mold, then prepare your vacuum and vacuum lines. So what it does, it pulls a vacuum, and then you have an extra vacuum tube, which you go into your resin reservoir, and that gets pulled in and sucked through the material. With carbon fiber and air you have to use an intermediate material to actually get it to flow better. As you can see, as they're doing back there, that's going to be a carbon fiber piece. That red material on top is made of nylon, and that lets the resin flow better throughout the whole thing. Throughout the whole, dry fibers. For fiberglass, you don't really need that because, as I said earlier, it has better permeability. The other way to make carbon fiber, to make composites in a mode, is called wet layups. What that is, you prepare your mode, and then you put the carbon fiber in by rolling up the resin onto each layer as you add it, and then pull the vacuum to infuse it. That's much messier. You have to deal with a lot more fumes, but it's a lot less. It tends to be less complex than vacuum infusion, as you only have to deal with the vacuum instead of the resin intake. But vacuum infusion does have some. vacuum fusion is a bit more complicated to do it. I just have to prepare those extra lines. But with vacuum fusion, you have a lot more time to work and prepare those more complex lines for resin and vacuum, because you don't have to actually prepare your resin until you get everything prepared, because it's such a real. With the wet web, you have to have your resin ready, and that greatly limits your time to wet. I have a few demo pieces here I'll hand out, just to talk a little bit more. This, for example, this is made of 2 pieces of carbon fiber and then a sandwich intermediate, which is, as you can see here, it's just like almost honeycomb kind of patterns. That allows you to have a lot more volume without having like to stack tons of layer of carbon fiber, and it's still really strong altogether. This is similar to the telescopic arm, smaller pieces of it, because we ended up looking at carbon fiber instead of finding it. We wanted to use specific shapes to actually do it how we wanted to. And then I have another demo here, well, 2 different demos actually. This revolving around composite materials, just so you can better visualize how they work. I'll start with this one, this is styrofoam. I have 3 pieces of styrofoam here. One has tape on one side, one has tape on both sides, and the last one doesn't have any pieces of tape.
Really strong.
As you can see, the one without any tape on it is very easy to just break it out. It snaps like that. Pretty much no resistance to it. As for the one piece, if you try and break it with just tape side, it's a lot harder to because it bends and that distributes the force better instead of just snap it. If you go on the other side where there's no tape reinforcement into it, it snaps just as easily. And then lastly, the one with both sides on it, it's very hard to break, it's much stronger, it just kind of bends instead of snapping. This is very similar to our fibers over here, to carbon fiber and how it works. With the tape in this case being like your polymer, because it helps distribute the load of the whole thing, while styrofoam gives it volume and like shape and structure. And then I have another, I'll put this one on the front table so it's easier if everyone can see, and then you guys can come mess with it if you want to. This just shows, I have a few different pieces of carbon fiber here. This one is a drill, this one's unidirectional, and then this is aluminum steel right here. So what I just want to show you is the strength, resistance to bend it has. So this carbon fiber piece is much lighter than this aluminum one. And if you check it here, I press down on it, the aluminum is a bit harder to bend than the drill. But if you use the unidirectional piece to try it, which is also lighter than the aluminum, it's stiffer than the aluminum piece. So it's strong in that way. However, compared to the steel, which is much heavier than the carbon fiber pieces, it is better at resistance, but it costs a lot more weight. And then these are just carbon fiber pieces if anyone wants to see them, carbon fiber parts. I think we also sent out samples of different reef patterns there. Let's look at those. Do I have any questions? Anything anyone wants to know about carbon fiber or just composite materials?
How do you determine how many layers of the carbon fiber are made up?
That just kind of depends. It can depend a lot on things like how thick you want it to be, if you're using like an intermediate like that. Here's just what a solid piece of carbon fiber will look like with lots of layers. But that's also determined on your reef pattern, because I think one of the samples we sent out showed 2 unidirectional pieces and a 45 groove. So you can change when you're making it, but when you stack it, that orientation can also determine how that force is exerted. So it just kind of depends on what's best.
You can also, like, obviously both of these are thicker than any, like, one layer like this, or just a few layers. But this one is way lighter, but it's a little bit less strong than this one, which is like pure carbon fiber. And then this one, it has like the kind of hexagonal like matrix in between to make it thicker, but it's way lighter than this.
Like, well, our team are trying to really prototype a gripping mechanism for our robot was made of what, like 4 sheets of carbon fiber?
But yeah, like 2 or 3 on top and then a foam forward and so.
Yeah, and it was about like an inch wide, but it was only made like 6 sheets of carbon fiber total because we used a big piece of foam as an intermediate piece between it. So it depends on what you want it to do and how strong you want it to be. Any other questions?
One of the things that this team is doing is there's part of I'm from the same foundation too, so that they put out a video series on how to do composite materials. What they're doing is developing them just as kits to go along with it. So if you want to participate in that, that's what they're trying to do. Saying it'll be a program with the next year or two that will help them learn, help teams understand and get access to composite materials. That's what they're trying to get on today. To show here's some options you guys might be.
Does it cause any problems if we like drill through the carbon fiber?
You just have to be a bit careful when working with it because it does tend to be very brittle, and you should very restorate it when doing something like that because they can release small fibers which will act like vessels if you breathe in them. Similar to vessels, they're small fine particles. So very restorated, recommend a flat area, and just be really careful on doing it.
For these dust masks. And that respirator, the big respirator, no, just because you're dealing with the dust, so the dust mask would be acceptable.
Just better be safe. Yeah. Any other questions? I think that's all I have.
I already mixed the resins, so you move that pretty quick.
Yeah, so here's a demo of the bag. This is vacuum infusion process, like I mentioned that. It's just making a flat sheet of carbon fiber. So, we have this,
Because Brandon isn't here.
gather around, I'll just walk us through this. So, starting from here, this is our resin, like 2 pieces, mixed together, all activated already in there. This is the tube, this is our resin intake. We'll take it in through a spiral tubing through here, which will release it across the whole material. This is a flat piece of carbon fiber we're doing. This is the red nylon intermediary I mentioned, so it flows better through it. So once this is put in there, it'll go through the whole object, saturating it, and then through here into our vacuum line. This vacuum line goes into what's called a resin trap that intakes all the excess resin, leaves it in there, and then out of the resin trap goes just air into our vacuum pump right here. And then I think it's ready to go. So what they're doing now, they're just preparing, taking the tube out. Whoops. And then once that's put in, the epoxy resin will flow through the carbon fiber piece, saturating it, and then it'll be cured in like a day or 2. So it's just ready by, my actual starts back on Monday. You don't just have to make 2-dimensional shapes with carbon fiber. You can use things like 3D printed molds, depending on what kind of piece you want to make.
So obviously, if you have a leak, you can get lots of bubbles in there.
Yeah, we've got a leak somewhere, so we've been fighting it all afternoon.
There's just that one spot. So one spot up on the outside.
Let me just press down on this, try and close the leak. This is one of the hard parts of the vacuum infusion process. Because the resin's not already in the piece, you have to do this, which just adds complexity with how you set up your vacuum bag. So you sacrifice some things, you add a lot more complexity to have more time to be able to vacuum your piece and get in a position you want. So we could spend the time fiddling with this and crush by pressure or time just trying to get it ready before we vacuum it. we could go ahead and prep and then make our resin, and then it'd be good to go. Which isn't something you can do with just standard wet layout. Any questions about this setup?
Do you have like excess on the sides, like on this side especially, that doesn't get resin in it?
It just depends.
This shoot 2 days ago, this one.
Yeah, like we tried making a piece of this one. We tried having it cover the whole piece. We had our resin inlet here, but what happened was the spiral tubing was too long, so it channeled into the sides and only covered this with resin instead of that.
There's also a peel ply
Yeah.
that goes on top of this. So the carbon, it goes carbon fiber and a peel ply. The peel ply separates out the resin from this top part. So you peel that off once you're done. You get in there with just like that carbon fiber panel over there on the left is one of the ones that we made. That one too. That's the one we just made yesterday.
You can see some of the issues with it.
Yeah.
Yeah, so here you can kind of see where like the
Resin
air
didn't get to it.
would not hit that full flow.
We scrambled this one, to get this one done, so we do have a few leaks in there. But what the future of the kits will have, which will have is you get a box, it'll have all the vacuum bag material and things like that, and we're still working on the vacuum pumps and stuff like that, how we get those donated to the cause. So and I try not to talk with these guys all the time because there's two things I'm very passionate about in the world. One of them's first, the other one's composites. So I'm very excited about this program with First Robotics. I'm on the SAMPE board, the SAMPE Foundation board. SAMPE Foundation board is their STEM outreach for SAMPE. SAMPE is the Society of Material Process Engineers, so they're the big organization for composites for mostly aerospace and stuff like that. So we're excited to be participating in this program, and I've had long conversations with First about getting composite parts in their kit parts. So we're working on that. So this is the first stage. Yeah. It's a little hard to do FOL.
Yeah.
So in the future, there might be more, we can get kit parts or make, one of the things that we're working on is getting materials available for, we've got, so if you want to talk about that a little bit or not, so where we're getting, both donated material and, we got to leave somebody keep it running. So just be aware that there might be options in the future that you guys might be able to get access to some of these materials through this program. If you have interest in it, talk to these guys.
Oh yeah, our team would have really benefited from having some lightweight pieces last year because our armature was a little heavy.
Well,
So we
grab
burned
the
through-
tube.
we burned through
Grab one of the little
those
tubes. The long tube, not the big one, but there's in there a little, yeah.
Yeah.
That's part of our wonderful excitement.
There's an example of like one like UV carbon fiber tubes, nice and light, nice and strong. If you want to see that.
So those are, and one of the things that we're working with these guys to do is help design like a telescope, like a better version of that telescoping tube over there. But, for the FTC team, the little ones, we can get access to working, through my contacts to say, okay, companies, let's get some materials donated to the cause here. So,
At the FTC level, I don't think any of the fonts that I was going to experience would actually break any carbon fiber fonts.
Yeah.
So
Yeah, for us it would have just been weight
Yeah.
reduction. Right?
And that's what it's good at.
Key things for us.
and that's, the especially like arms and stuff like that. So you could really, that stuff, you don't have robots, half the time see the big robots are flipping over all the time. It's like, okay, if you had lightweight materials up at the top.
it wouldn't flip.
Yeah, ours was just
You gotta hold it all night now. You got, that's you. You're in charge of that leak that you made. We're gonna blame it on you.
That leak?
No, this leak. That was my problem. I had to do that one.
I thought I had it, honestly. And then if I leave it alone for a couple of minutes, it just comes back.
Anything else? Any anything anyone wants to know about composites?
Anyone want to take turns holding this leak?
Again, reach out to these guys if you guys want any information regarding the future about, what, if you guys want to participate in this program they've got, they'll be, just reach out to them.
I think we're done. Thank you.
Okay, I need somebody to give me some duct tape so I don't have to stand there and hold this thing.
I'll go grab that tape.
Okay, there's a roll over there, I think.
Yeah,
Update.